Okay, can you see this slide? Hello? Can you hear me? Okay, now we can talk about the herbicide selectivity specifically for atrazine. So we want to talk a bit about atrazine metabolism and its selectivity. You know, atrazine is widely used to control weeds in maize. Uh, its molecule has got a chlorine atom. So we talk of chlorinated triazines, which can undergo hydrolysis at the chlorine atom on carbon number 2. Hydrolysis involves the replacement of chlorine by an OH. We know in some herbicides, this process is catalyzed by cytochrome P450. In the case of atrazine, the enzyme which catalyzes this process is known as benzoxazinone or Dimboa instead of cytochrome P450. But some people think that cytochrome P450 may also be involved. So the result is the formation of the addition of OH group to the atrazine molecule. It becomes hydroxyl triazine, which has no herbicidal activity. Probably this is how atrazine can be detoxified uh, in maize plants. So we are talking of this process where chlorine is converted to OH. Here we have simplified it, where we have atrazine with chlorine being converted to OH. And this is the 2-hydroxy atrazine. Now, instead of cytochrome P450, sometimes we have a Dimboa as the enzyme catalyzing this process. At two positions, that is carbon number 4 and 6 on the atrazine molecule, the process of any dealkylation will take place. And of course, this is facilitated by cytochrome P450. And the functional groups which are removed from this molecule are NHCH2, H5, NHC3, H7. These are here at the bottom, and they can be converted to NH2 for both positions, or we can simplify it like this, where we have the two positions now being occupied by NH2 after N or nitrogen dealkylation. Again, atrazine can also undergo conjugation reactions with the glutathione, what we call atrazine glutathione conjugations. And the enzyme which is involved is glutathione S transferase, which allow glutathione to conjugate directly with atrazine, and as a result, its herbicidal activity is lost. And probably this is how selectivity can come about because of these biochemical reactions. This then is the atrazine which is conjugated to this glutathione, which contains three amino acids, and it is the cysteine, which contains SH, which will then combine with the rest of the molecule of atrazine at the sulfur bond. This could be a simplified version of the atrazine glutathione conjugation reaction. Atrazine plus glutathione, we can represent atrazine using this, and this is the glutathione with the reactive component, the SH. Then we form this part where atrazine is now attached to this glutathione. And the glutathione S transferase enzyme will facilitate this reaction, thus detoxifying atrazine. It could be within the maize plant. We want to look at the conversion of some herbicides from non-toxic to toxic form. For example, we can have a formulation or herbicides which are not toxic in their original state, like 2,4-DB, MCPB. These are not phytotoxic. But as soon as they enter the plant, they are converted to 2,4-D and MCPA respectively via what is known as beta oxidation. So plants which are capable of converting these non-phytotoxic forms of these herbicides will eventually get killed. So selectivity is based on the beta oxidation. Those which cannot oxidize these herbicides are not killed. This is the real 2,4-DB, which is beta oxidized to form an acid which is toxic. We do have some herbicides with a potential to kill crops, but there are substances known as surfactants or protectants which can be formulated together with these herbicides to aid selectivity. We find these herbicides among the thiocarbamates and the chloroacetamides. For example, EPTC is a surfactant added to it, known as diclomid, which is incorporated in the herbicide formulation so that it will not kill maize. EPTC without diclomid will damage maize. We also have metolachlor or jewel, which can be applied to sorghum. For jewel not to kill sorghum, it should be formulated with a surfactant known as concept. So you have, in fact, if you are buying jewel for sorghum, make sure that that jewel has got a concept or a surfactant. Otherwise, if you buy the usual jewel, it's going to kill your sorghums. Lasso or anaclo is a surfactant known as flurazole, and you can use it in sorghum. Acetaclo has got a surfactant known as oxabetrenil in sorghum. So it is these grass killers which need surfactants if we are going to use them in maize and in most cases in sorghums. But concept is quite common in metolachlor so that we don't kill our sorghums. So how do the seveners work? Probably they increase the metabolism of the herbicide. For example, they could increase the levels of glutathione and the glutathione S transferases or cytochrome P450 enzymes, which can facilitate breakdown. Let's talk about antagonists. There are some chemicals, like basagran and fusilade. Both can be used in soybean. For example, we can use basagran to control broadleaves, whereas fusilade can be used to control grasses. It may make a lot of sense since these uh, are all being sprayed to soybeans. You may think probably the best is to mix them. But if you mix them, because these are antagonists, uh, you may lose uh, weed control. So you may fail to control your weeds. So some herbicides, when applied as mixtures, have reduced activity. So you will fail to control your weeds if you mix basagran and fusilate. Synergies, these are chemicals. If you mix them, for example, nicosulfuron, uh, if it is mixed with an organophosphate insecticide, or probably the tank has not been cleaned after use of an organophosphate, it can lead to injury of crops. So some herbicides have increased effect if they're in the presence of an insecticide. For example, the combination of nicosulfuran, NAB plus organophosphate insecticide. So we should make sure that our tanks are thoroughly cleaned before we use some of these pesticides. Yes, just a straight summary on selectivity. It's very short. What we discussed on selectivity was differential penetration, differential translocation, compartmentalization, sequestration, altered binding site, differential metabolism, that is phase 1, phase 2, and phase 3. Then we have just talked about the conversion of herbicide from non-toxic to toxic form. Remember 24DB being converted to 24D, MCPB being converted to MCPA via beta oxidation. We have got the inclusion of safeners or protectants in some grass killers like EPTC, metaraquilo, anaclo, etc. Antagonists, these are herbicides. If you mix them, you lose herbicidal activity. Synergists, it's a mixture of pesticides which can produce undesirable results. For example, if nicosulfuron is mixed with an organophosphate, or probably the tank was not thoroughly cleaned, you may end up killing your crops. So this is it on the selectivity, and we wanted to talk a bit about atrazine. So I'll stop here on selectivity.